Welcome to Brain Vision.
Okay, so here's the setting of this problem. We have a tungsten sphere suspended within a vacuated chamber. So this chamber, we have a sphere suspended in it, and the chamber is evacuated. And the radius of the sphere is 1.5 centimeters. The wall of the chamber has a temperature of 290 K, and the tungsten sphere has a temperature of 3000 Kelvin. We know that the emissivity of tungsten is 0.35, and the question is, what has to be the power that is applied to the tungsten to maintain the same temperature as the tungsten comes to thermal equilibrium with the photon gas inside the chamber. And so this is how we do it. This is how we would do it. So we have to recall Stefan Boltzmann law. The Stefan Boltzmann law says that the heat current is equal to the emissivity multiplied by sigma, which is Stefan Boltzmann constant, multiplied by the area of the sphere, and multiplied by T to the fourth minus Ts to the fourth, where T is the temperature of the sphere and Ts is the temperature of the surrounding. And so we simply just plug numbers. 0.35 times the value of the Stefan Boltzmann constant is 5.67 times 10 to the negative 8 watts per meter square Kelvin to the fourth, multiplied by the area of the sphere, which is 4 pi times 1.5 divided by 100 square times 3000 to the fourth minus 290 to the fourth. And if you plug in numbers, you would get 4.54 times 10 to the fourth. So here is the power that has to be applied to the tungsten sphere in order to maintain its temperature. So Stefan Boltzmann law says that the rate of power dissipation is equal to epsilon times sigma times A times T to the fourth. Where T is the temperature of the object, A is the area of the object, and these are just constant, and sigma and epsilon are just constant. And so the first term here is the rate of power dissipation from the tungsten sphere. The second term is the rate of power dissipation of the photon gas into the tungsten sphere. And since we have two opposing flows of heat, then we must subtract the second from the first in order to get the net heat flow from the tungsten. And in order to maintain the temperature of the tungsten sphere, then we need to apply the exact same net heat flow into the tungsten sphere to prevent it from losing energy and thus losing temperature. So that's the answer to this problem.